And thank you for the invitation. And it's an honor to speak here in this big silent disco. I want to talk today about, like I said, technical challenges in weed mapping. So what is weed mapping? We are mapping weeds in fields, so all the plants that shouldn't grow there but that grow there, and help farmers to fight them more efficiently. In the beginning, I want to talk a little bit about the company, same dimension, and then I will explain the spot spray technique that we then can do when we detect these weeds, that we only treat the weeds where they actually are in the field. And then I talk a little bit about our camera technology that we developed to achieve this. And then in the beginning, in the end, a little bit about the direct georeferencing and the required accuracy that we need for our system there. And finally, a little bit about the challenges that we are facing when we want to automate the flight planning for the drone. So a bit following the discussion in the very morning of this conference here. And finally, I just show a few examples of the spot spray mapping. So how does this actually look when we detect the weeds and when the farmers then treat them? So my introduction, I'm Philipp Schneider. I'm engineer at SEM Dimension. Before I was working at the Institute for Photogrammetry in Stuttgart. SEM Dimension is a small agri-tech startup. We are currently a team of 15 people. So when this picture was taken last year or 2 years ago, we are a bit smaller. So we are hiring people right now. And we are a diverse team of agronomists, data scientists, spatial engineers, botanists, sales and marketing, pilots and annotators there. And what we are doing, like our main, what we're doing is that we rapidly map fields with our drone technology, then detect plants in there, so single plant detection, and then provide maps to the farmer that he can treat the weeds directly in the field where they are and only where they are. So this is kind of nicely shown in this video. So you see usually this long boom here with all these nozzles would be spraying constantly, but with a map from us, it only sprays where actually weeds were detected before in the field. And this helps to obviously save up to 95% herbicides with the effect of saving money, but also low environmental impact on the field and on the surrounding environment. What you don't think of usually is that you also harvest more, because these herbicides, they also harm the crops that you want to grow bigger. And what you also can do with this technique is that you can target plants that you could not target otherwise. So you can selectively target the plants by the way they look and not by their biology, how they work basically. So one example for this this effect, phytotoxicity, is that you see this field of sugar beets here, and some of them are a bit smaller than the other ones. This is actually where we detected weeds before and where the sprayer had to spray. And therefore the sugar beets there grow a little bit smaller, but only where actually weeds were detected before. And the rest can grow bigger. The other side, you see some potatoes growing in the middle of sugar beets. And this is a good example for the specific targeting of plants, because you could now target these potatoes that come through from last year, so from the last harvest, directly here, so they don't carry over disease to the next crop rotation when you want to plant potatoes again. The mapping system that we developed for this, you see here this camera under our UAV system. I drew here the Castor building. This is one of these high buildings out here, so you can see how high our drone flies. It has a working height of 60 meters, and at 60 meters we can map the ground at 1.6 millimeters ground sampling distance. The camera, you see this multi-head system, has built-in 6 camera heads that then map out the ground. It has obviously RTK, since we are going here for direct georeferencing, because here this time is really money here. We cannot go in the field and put ground control points there. the drone has 30 minutes of airtime. And with that combination, we can achieve 60 hectares of mapping at this 1.6 millimeter resolution, or 15 hectares per hour if you go for half the flight height. The drone or the camera built-in has some edge computing to pre-process the images, because we're dealing with a lot of data here per minute. We come to this later. Maybe a little look at the camera. It's, like I said, this multi-head system with an overview camera and carried by a quite large drone. So this is right in the sub 25 kilograms category. So the system is 24 and something, carrying 2 big batteries and our camera underneath. And the wingspan here is 2 meters something. So it's basically bigger than me if I lay on the ground. The capability of this, a little bit in numbers, is the slide is from last season, so there was one season in between. So season, I mean most of the herbicides or plants are treated when the plants are growing and are young. So 60% of our flights are happening in May. And we took there in this, like in the last year, but 60% of these images, 60% of these 3.7 million images we took in May there on more than 1,200 fields or something like this, 1,200 fields. And I roughly calculated this is, we mapped the area there of Stuttgart, of a major city here, in 1.7 millimeters, just to compare the area that we mapped here. Or if you would go to a 9 centimeter ground sampling distance, this would be already the entire area of Germany. And you see we are mainly active in Germany right now because we are coming here from the south of Germany, but we also have some customers in Czech Republic, some in Hungary, and we have one system flying in Lithuania. Maybe a little bit the workflow, how the mapping works with our camera is that you have your plants growing in the field, and the camera is with this drone system mapping there, and there you could say like the raw sensor data is something like 200 gigabytes per hour that comes up there, gets pre-processed by the camera, and then after you flight you plug in the hard drive and you upload all this data to us, which is then roughly something like 7 gigabytes per hour, and then by hour I mean here flight hours. So every flight hour with the system generates 7 gigabytes of data. We then in-house process this data and send the farmer or the customer back a map, this prescription map that they can then put on their sprayer. So they don't need usually new techniques, for, new sprayers or anything for this, because usually the sprayers are capable of doing this, but they don't have the maps. Exactly. So I wanted to had some technical challenges I could choose from to talk about, but I only want to talk about the 2 last ones. So, but maybe mention a little things that gave us headache in the last years was different GPS systems between our drones and the farmers. So usually, like we fly with, for example, in Germany with Sapos, or in Lithuania with the equivalent there. But some farmers, for example, have their own RTK system set up. So, and they are just somewhere, and you have to go there in the field and measure that offset, because they usually drive with the same machine. So as long as it's repeatable, they don't care about where actually their field is. If this is 1 meter left or right from ETRS 89, they don't care. Then you have different map formats. So these, you can think of these sprayers like a very big 3D printer, and they take one format and then they spray there. But there are actually like 15 different manufacturers of those, and each of them has a slightly different format. And we are working together with those to like unify this format, because, like I said, these 50 megabytes per hour of data, usually these sprayers are not made for doing this. So they are usually made for, you upload a shapefile in there that says spray inside of this field, and that's and not millions of plants on a big field. Then this is more internal in the company, this big data handling. Like I said, these millions of images that we are taking and data points, and also then the maps we create. It's challenging to just have this data, look through it, find stuff again, and just save it and backup it. A bit my part, but is the label domain for computer vision. So let's say a sugar beet doesn't look the same all through the year, so it's not like a, I don't know, cat that always looks the same, more or less, when it's adult, but it changes very rapidly through these 3, 4, 5, 6 months once it's growing. So really, you have to gather a lot of data over time here. What I want to talk about is this direct georeferencing a little bit and the required accuracy that we need there, because we don't have this, like I said, we map everything with 1.2 or 1.5, let's say better than 2 millimeters ground sampling distance, but we don't need this accuracy here, and we can take some shortcuts here for achieving less data there. And the other thing is the challenges in automatic flight planning. And we had this topic in the morning that there are, for example, windmills on the field. And if we want to automatically plan these flights that the drone does, we need a source for reliably having a source for these windmills in the field. Not only windmills, there's also power lines and, I don't know, airports and other restricted areas. But like windmills and power lines are really critical because otherwise it crashes. So the direct georeferencing, the challenge here is mainly to, you have your drone in the air with a precise RTK system, and these mapped images on the ground from the camera head, and then you detect your plants in the image, and you need to somehow map then back these detections in the image on the three-dimensional ground. And not going here into how we do this, but we did some experiments, and because we always have to be accurate enough for the sprayers. And some experiments, we continuously do these experiments, is that 90% of our ground measured points, so we have these red dots here, that we then mark in the image and try to reproject in the real world and see how good we are. And 90% of them are better than 10 centimeters. So this is roughly our accuracy, how good we can determine a point on the ground from this system, which is a bit contradictory to if you do normal photogrammetry, like with your DJI and with your 80% overlap, with basically only one camera, then you can achieve an accuracy in this millimeter range, like in the same, like your pixels. But we designed our system to be faster here and go only for the resolution, but not for the accuracy. So what accuracy do we actually need? So in the end, we are determined by the sprayer, and you see this is one of these booms by the sprayers, and they usually have 25 or 50 centimeter section control. So even the nozzles, they are distanced 25 centimeters, but usually they turn on 1 or 2 or 3 at the same time. So as long as we are better as a few centimeters, so the sprayer sprays 25 centimeters anyway, and we give a little buffer because the actual accuracy of the sprayer, this is the more challenging thing than our detection on the ground. And we usually buffer every point that we have some 60 centimeters, not because we are not sure that the point is there, because we are not sure if the farmer calibrated the system, the tractor, but the system, this big 3D printer, basically correctly. Because it starts with the GNSS antenna, and then you basically have leather arms, very long leather arms going to the side. And this has to be calibrated inside these, we call this display that is the computer that controls this entire system. So it takes the GPS, takes the driving speed of the tractor, and then turns on the nozzles a little bit before they reach this point and turn them off after they go over. And this is like a hydrodynamic system, so there's water flowing, so you cannot turn it off suddenly. So you deal with this entire system here for the required accuracy. And so usually we do some 30 centimeters, so 60 centimeters diameter around each plant that we detected. And we can reliably hit the plants like this if the system is calibrated. Some challenges in the flight planning. So obstacles for us are trees in the field. So we fly with an altimeter with LiDAR. So we cannot fly over trees because otherwise the drone goes up, because then we can keep these 60 centimeters on rough terrain without any terrain model in the flight planning. And you have power lines in the field usually that are also roughly in this height. and wind turbines. And I want to quickly compare two sources for this data. One is OpenStreetMap and one is this official platform dpool. We talked about this in the morning. And OpenStreetMap works very well in Europe. It doesn't need any license, but it's not guaranteed to be complete. It's not a source of truth that you can use. On the other side, you have this official platform, and they say we cannot commercially use them. We have to investigate how far this restriction actually goes. And it only contains major power lines and offshore wind parks, which makes it completely unusable for our application. What it is nice for is seeing airports around you. So we have this little field here, this blue-yellow thing. And this on the other side of the river somewhere is a small airport. And so we can already consider this in the flight planning, that you have to call the airport and tell them we are flying here around 10 o'clock in the morning. Yeah, also maybe short in time, we skip this a little bit. This is Frankfurt. Like you see all these colorful overlays here. So not the Google Maps dots, but these other overlays. These are restricted flight zones that you shouldn't fly in Frankfurt. But usually on fields, like I showed before, it's not so critical. It's mainly airports, wind parks, and power lines. So I have one example of how to plan around a power line, and this is this dpool information source that should actually provide you with this no flight zone. And you see here, these yellow areas here, they say don't fly here because there's settlement, but they don't show the windmills. The windmills are only shown in the overlaid OpenStreetMap base map here, what they use, but they somehow don't show all the windmills. So long story short, we have to work with Google Maps, with OpenStreetMaps here, and not with the official platform because it's lacking data. Finally, this is how a map of us looks like. So you see all these the pink areas. Each of the pink area, each of the little dots, is a 60-centimeter spot around a detected plant. And you see how these plants, they don't grow randomly, so they form clusters. And this is what you use with the technique. If they would be random, you also have this boom control and the section control, then it's hard to save something, but usually they grow in these big clusters, and that gives then the actual savings. This is a field from last weekend that we flew, or that one of our customers in Lithuania flew. This is 60 hectares, so I drew a little soccer field up there next to the scale bar. So, and this is 500 meters, so it's a very, very big field, and you see how spaced our flight plan is there. So you have 50 meters between each section, or 40 meters here with some overlap. And the outcome then there, they were growing canola there, and these are the thistles in the canola, and they could save up to 75% there. Maybe quick, we don't only map weeds, we can also map your sugar beets. So if you're interested in how dense are your sugar beets growing on the field, or what is your crop prediction for next year, but also if you're a breeder of sugar beets or of any crop, you can come to us and do research with us. So you say, in this plot I have this in this trial, and we then give you the numbers of how distributed your plants per square meter in each of these plots are. Little side business is soccer field mapping. So we do this with a greenkeeping company. There we fly, or they fly, with a DJI Mavic Pro, so with this multispectral sensor image. It takes 40 minutes per hectare to map, so quite long. So they take per football field something like 30 minutes. But therefore, this drone is much more accessible on these narrow football fields. Let's imagine you fly in a stadium. You don't want to fly with our big drone. Little outlook. We try to sell more systems in the next year and come towards this digital twin of your field, that you know what is growing today, what was growing last year, and maybe can predict what is growing in the next year. You can meet us in Agritechnica next month in Hannover, and thank you.